Greetings! In this video we're going to learn about integrating in polar coordinates. Here's a warm-up slash motivating example. Try to calculate, maybe this is exercise 1. Try to calculate this integral. So we have a vector field given above, negative x squared y, xy squared, and then a curved unit circle centered at the origin. And there are two ways that you know how to calculate this integral. One is you can parameterize c and then use the definition. The other thing is you learned about Green's theorem last time. So I would like you to use Green's theorem. Okay. So use Green's theorem. If you use Green's theorem, then you don't have to parameterize c, right? Then we get a double integral over some region, d. d is the unit circle. Then there's some integrand in there, then dA. I would like you to fill that out, take the curl and so forth, and then carry out this integral for a bit. So this is equal, then integral from -1 to 1, integral something, maybe dy dx, and then calculate this a bit more until you get a single variable integral. So pause this video and try it in your notes and get enough, do enough to get to a single variable integral. I'm gonna write out the single variable integral, but you should do the work to get there. So I got something like this. I'm not entirely sure if it's right or not, but something like this. And that looks really ugly. I could give this to a Calc 2 student to calculate, but I don't really want to. No one should want to calculate this integral. Perhaps there's a better way. Notice that this region is circular, so perhaps we can use polar coordinates, and that's what this is hinting at. Right? So hopefully with this you can see that after learning Green's theorem, you naturally want to be able to integrate double integrals in polar coordinates. And so here is how we're going to do that. Now suppose we're given some polar rectangle. It's a rectangle in polar coordinates. Let's call it R for rectangle. It has, remember, polar coordinates R and theta, and let's say R is between P and Q, and theta is between alpha and beta. Now let me draw a picture to go along with this. We are still in the xy plane, and then, well, I'll have two angles, alpha, and another angle, beta, and we'll draw two circles. Here, this is P, and this is Q. So the region we have is in here. This is our polar rectangle R. And suppose we are trying to integrate a double integral over this polar rectangle, f of x, y, dA. Now, as usual, what we would do is we would chop this region off into pieces. So let me draw this again. Alpha, beta, P, Q, and then we'll chop this region in a lot of subdivision. So let's say alpha is theta 0, and this is theta 1, maybe theta sub j. Eventually we get to theta, let's say m. So if we subdivide this into m parts, and also subdivide p between p and q to n parts. Let's say this is r0, and this is r sub n. but then we subdivide in here, r sub 1, r sub I, and so forth. Now we can get, let me see, r sub I is right here, theta sub j is right here. So here, let's see, let me color in this little piece. That piece, let's call it r sub ij. So what we would usually do is let this equal to limit as the number of pieces go to infinity in both direction, n and m. And then we would sum up what we get in each region. Sum I going from 0 to n, j going from 0 to m. And then we would evaluate, pick a point in there, evaluate f. Let's pick a point in there, x sub ij, y sub ij. So let's say x sub ij, y sub ij is in this rectangle R. We pick a little point in there, evaluate f, and then we roughly treat this little piece as constant. So f, we only need to sample at one point, and then multiply by the area of that region, area of r sub ij. Now what we need is to know the area of r sub ij. So what is the area of that little piece? So let me draw this piece bigger. So you've seen several pictures like this before now, but this one is a zoomed in version of that piece. Okay? So this is theta sub j here. This is theta sub j minus 1. This is r sub I. This is r sub I minus 1. I need the area for this piece. So this piece is r sub ij. Now let's pretend that this is a rectangle. I know it doesn't really look like a rectangle, but let's pretend this is a rectangle, like a rectangle like this. So then I can get the area. So then area of r sub ij is roughly equal to the width times height. Here width is easy. Width is ri minus ri minus 1. I need to multiply by this length here. Okay? But this, let me write this as delta r, the change in r. So you might then be tempted to say that this length here is the change in theta, but that's not quite right. Think about, what if theta changes from 0 to 2 pi? Then we get the entire circle. What is that length? That's 2 pi r. 2 pi ri. So notice that we'll do some scratch work here. If delta theta is equal to 2 pi, if theta goes from 0 all the way to 2 pi, then this length here, this arc length here, then arc length is equal to 2 pi r sub I. Yeah, you know this formula for the circumference of a circle from kindergarten. So what if delta theta is pi? If we only go halfway, then the arc length would be pi r I. Yeah, we only go halfway. What if it's pi over 2? Then it will have pi over 2 here times ri. In general, it's delta theta times r sub I. That's the length here. So here, this length is delta r, but this length is ri times delta theta. This is very important to note that here, this length does not depend on theta, but that length depends on r. So one of them is just a change in r, the other is change in theta times r sub I. This is very, very crucial, and that's why I really want to explain this in detail in the video so you see where this r sub I come from. Otherwise, you'll never know why there's an r sub I there. So then we multiply this by r sub I. Now, let me just write delta theta. So this is width, this is length, or something like that. So this is equal to r sub I delta r delta theta. That's the area for a piece. Then we can put it in here. So let me write this over. So this is equal to limit of sum. I'm too lazy to write out the details now. Okay. Of f xij yij, and then the area is ri delta r delta theta. And so now we recognize this, now that it has delta r and delta theta, as a double integral. This is equal to an iterated double integral. I'll fill in the details later. Okay. And then now we drop the sub i's and j's as usual. F x y r dr d theta. The delta r and delta theta turns into dr and d theta. R sub I, the I is dropped, and then we get r. F of x sub I j, y sub I j, the I and j's are dropped. You get here. And then we need to know where does r go from? R goes from P to Q. And theta goes from alpha to beta. And since everything is in terms of r and theta, let me write one more version where we have everything in terms of r and theta. So f, what is x? Remember, in polar coordinates, x is r cosine theta, and y is r sine theta. And then we have r dr d theta. And so if you want to remember this, it's useful to think of this as dA. So a useful mnemonic device is to remember that dA is equal to r dr d theta. Now I could have, of course, started off by just giving you this formula, this mnemonic device, and be done. And that's how I learned calculus, by the way. And I never understood why we have to stick an r in there. Why doesn't dA just become dr d theta? If you compare this with, usually we have dA equals dx dy or dy dx. You can integrate in either order. Why does it matter when we are using polar coordinates? Why do we need a little r in there? Well, that r came naturally from this calculation of the fact that a polar rectangle's area is not just x times y, not just r times theta, but r times the change in r times the change in theta. So that little r here carries over, and now this is the formula we can use. Well, let's try using this formula and we'll see it in action. Now let's try our hand at this first warm-up exercise. Here, hopefully you figured out that's x squared plus y squared. So now let's start over. I don't want to use this, so I'll start from this part. So we've already used Green's theorem, and then we got a double integral, x squared plus y squared dA. And now I would like to use polar coordinates to integrate this. So then our polar coordinates formula says we need to turn the x squared into, what is x squared? Well, x is r cosine theta. This is x squared. What is y? Y is r sine theta. We're integrating this entire thing, and dA is r dr d theta. So here we have x squared plus y squared dA. That's r cosine squared, blah, 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 blah. And then r goes from something to something. We have a unit circle. R goes from 0 to 1. Theta, we have a unit circle. We go all around. The angle goes from 0 to 2 pi. So this is setting up the polar coordinates integration. Now let's carry this out so we see how easy this is instead of something as ridiculous as that. So integral 0 to 2 pi, integral 0 to 1. What is x squared plus y squared? That's r squared cosine squared plus r squared sine squared. That's just r squared. Yeah, your favorite identity. We don't have someone writing this on the sideboard, but you still remember, of course, cosine squared plus sine squared equals to 1. So we get r cubed, r squared from here, and then 1, there's an r from here, right? R cubed dr d theta. And we saw that when we have something as simple as this, we can pull it into two integrals, right? This part is a constant, so that's integral from 0 to 1 of r cubed dr. And then once we pull that out, this is a constant, integral from 0 to 2 pi d theta. So this one is a fourth. R to the 4 over 4, evaluate 0 to 1. This one is 2 pi. So we get pi over 2. You see how easy it is to integrate in polar coordinates? And that's because this problem is set up to use polar coordinates. Two signs. One is that the region is circular. The other is that you get x squared plus y squared, which is equal to r squared. So you might remember that from polar coordinates. And so that's why we should use polar coordinates when things are round like this. Now let's try another example. Here I have a 3D region, xyz, described by the fact that z is between x squared plus y squared and 8 minus x squared plus y squared. And then we want to integrate over this region, this function. Now, how should we go about it? Remember, usually what we do for triple integrals is to first get it into a double integral of an iterated single integral. And let me copy first x squared plus y squared. And now we usually integrate z first, and then this entire integral will integrate with respect to a area. What are the z values? Z goes from something to something described in x and y. Thankfully, we already have that description. So this one is given to us for free. We go from x squared plus y squared to 8 minus x squared plus y squared. All right. And what is d? Where d is the projection of w. D is projection of w to the xy plane. What is that? Well, these two curves intersect at some point, so it's bounded by the curve of the intersection of these two surfaces. X squared plus y squared equals 8 minus x squared plus y squared. In other words, if we move this to the other side, we get x squared plus y squared is equal to 4. Now I moved it to the other side and divide by 2. So that's equal to 2 squared. So what we have is, so the region that we care about is given by this. Inside the curve, x squared plus y squared equals to 2 squared. It's less than or equal to here. Armed with that, we can continue here. So then we'll use polar coordinates. Equal to integral. Well, let me write the thing inside first. Let's leave z as z. And what's x squared plus y squared? That's r squared, right? So the square root is r. This is x squared plus y squared. That's this part. We still have a dz. But then, so this is still dz. And then I will stick another r in here and then dr d theta, where the r dr d theta comes from dA for polar coordinates. And the theta goes from 0 to 2 pi. R goes from, well, the radius is 2 for this circle. The radius is 2. And z goes from x squared plus y squared, which is r squared, to 8 minus r squared. So now we fully set up the integral in terms of in terms of z, r, and theta. Now we're ready to integrate. As before, the outer integral is, because nothing depends on theta. It could, yeah, and you'll probably see that in the homework, but here nothing depends on theta, so I can pull the theta out. In the future, you can just write 2 pi directly, okay, but maybe one more time I'll write it here. And the integral 0 to 2 of here. If we integrate with respect to z, we get z squared over 2. R is r squared. And then dr. No more d theta. D theta is already here. Oh, and z needs to be evaluated. Z evaluated from r squared to 8 minus r squared. And then we integrate with respect to r. Right, so we substitute these in, expand it, and then it's a single variable integral with respect to r. I don't really want to do it. This is just 2 pi. I will skip to the end. This is equal to 1024 pi over 15. The final answer is not that important. I want you to grab the hold of the concept. So that's what we did, is change the triple integral to a double integral and a single integral. And the double integral, we use polar coordinates. But essentially what we did was that given a point in x, y, z, if we have a point here, x, y, z, we projected it down to get the point x, y, 0, and then we represented this point in polar coordinates with r, which is equal to x squared plus y squared inside the square root, and then theta, which is this angle theta right there, using polar coordinates. And then we still go up there using z. This is called cylindrical which is simply polar coordinates in the xy plane, and then we add on a z to get a height. So using cylindrical coordinates is really easy to describe things like water bottles because they're things that look like this. By the way, I was reminded that back in the day they used water bottles already. David was chasing. David was being chased by Saul, King Saul, and then David stole his water bottle, right, and said, "How could you let your?" And then told his servants like, "How could you let your master's water bottle be stolen?" Blah blah blah. Yeah. So anyway, this looks like a water bottle, and that's cylindrical coordinates. So if technically what we did is integrate in cylindrical coordinates, and then so we have dv is equal to r dz dr d theta. So we derived this with almost like no extra work because it's really just polar coordinates with a z component. Of course, you can also write this as r dr d theta dz, and in whatever order you would like. Yeah, but I would recommend leaving the r in the innermost part, even if you don't integrate it immediately. So that way you can recognize this as a triple integral. And that's why earlier here I awkwardly stuck r in there, even though it's dA, it's r dr d theta. I included that so that we have a standard notation for triple integrals. We just saw a three-dimensional generalization of polar coordinates called the cylindrical coordinates. Right now we'll also look at the spherical coordinates, but maybe before then let's recap cylindrical coordinates. So we have x, y, z, and we have a point which we drop down to the xy plane and then use polar coordinates. So x, y, z, we drop it down to the plane to get x, y, 0, and then convert to polar coordinates where this is the radius r and this is the angle theta. So we have that in cylindrical coordinates, if we have r, theta, and z, now let's convert to rectangular coordinates with x, y, z, and our conversion is x is equal to r cosine theta, y is equal to r sine theta. Those are from polar coordinates. And then, z is just z, and we haven't changed it. We can also convert back, and we need some equations for r and theta. R equals x squared plus y squared. We need to take the square root. Maybe I'll simply square r, and then we can solve for it. Similarly, for theta, we can, that's this angle. If we use triangles, then that's y over x if we take the tangent of theta. And again, z equals to z. So this is cylindrical coordinates. Now, let's consider a second generalization that's called spherical coordinates. The reason why I want to draw this here is so you can see how similar and different these two generalizations are. So again, we have a point here, and then again we drop it down to the xy plane, x, y, z, drop it down to x, y, 0, and then again we can use polar coordinates. So I will still label this with theta, and instead of saying this angle, however, we'll also draw this line from the origin to the point in question, and we will look at this length, spherical. You can't see the word spherical, means that we have spheres. We want to talk about radius or distance from the origin. So here, this radius, we'll use rho. Rho, it's like r, yeah? Because we already have r here, and we don't want to call that thing r. So that's rho, that's distance from the origin. And we are not going to use r, right? We use this angle and that distance. We need a third variable. We'll use this angle. So angle of declination, if you're standing upright in the z direction and then you bow down towards this point, the angle that you have to bow down is called phi. So those are the variables that we'll use for our spherical coordinates. So now let's say spherical coordinates. Let me summarize here. Spherical. So for spherical, we'll start with rho, and then also write theta and phi. Those are our angles. So rho is distance from origin. Theta is the same, so I won't label this. And then this phi is the angle of declination. You have to decline from positive z-axis to xyz point there, which I'll also write here, rectangular xyz as before, and that's write equations to go between the two. Let's go this way first, like before. So let's calculate x. What is x? Well, I think maybe I need to draw another picture, so I'll scroll up here, and then not scroll up, yeah. Okay, so let me draw a picture in this vertical sheet that starts here at r and then go up like that. So if I label this point P and label this point Q, I can draw a plane here where this point is Q and this point is P, and then that here, that's rho, and this is the positive z-axis. Can you see that? I'm sort of drawing this plane right here. That's the plane that I've drawn here. And notice the bottom here, that's the distance r. And this angle is phi. So what is r? In terms of rho and phi, this phi, you can also put it there. So you get rho times sine of phi is r. So then, if that's the case, maybe I'll simply write here from spherical to rectangular. So x is r cosine theta, but r is rho sine phi. So we have rho sine phi cosine theta. And then y will be rho sine phi sine theta. Now we go from r to r cosine theta and r sine theta. And what about z? Z is rho times cosine, of phi. Oh, that's the conversion from spherical to rectangular. Let's also come backwards to come back, we need equations in terms of rho solved the other way. So rho is equal to, we need rho in terms of x, y, and z. Rho is the distance, so we can use the distance formula, x squared plus y squared plus z squared, quantity square rooted. Maybe I'll simply write the square on this side. You can solve for it. Theta is the same as before. Yeah, tangent theta is equal to y over x. That hasn't changed much. And then how about phi? Oh, we need an equation in terms of phi. I see here z seems to have something in terms of phi. The cosine phi is z divided by rho. Cosine phi is z divided by rho. Now rho, of course, is not x, y, z yet. You could write this out as square root of x squared plus y squared plus z squared. Quantity square rooted. Solve it, put it here. If you want all x, y, and z on this side, if you're a purist. I like this one because you probably would have solved for this anyway, so this would have been a number that you can use right here if you're converting back and forth. Now this is an introduction to spherical coordinates, and these are good for describing spheres. So how will we integrate in spherical coordinates? As you can see from the time of this video, I'm almost done. The reason why I'm almost done is because to derive the formula for integral, what we would need to do is to look at what happens if we increase rho, theta, and phi a little bit, and we'll get some kind of weird shape, and you can see it on your textbook, like right here. Sorry, I can't turn it because my document camera's body is in the way. Okay, but you can see this weird shape right here. And you can use geometry to calculate that volume estimated, just like how we did it for polar coordinates. That's too complicated. The details are in the book, so I don't want to go over it. And also next time we're going to see a general approach for doing these kind of things without using so much geometry. So instead, I will simply tell you the mnemonic, also as a summary. Okay, so here's summary of today. We started with dA, and that's equal to dx dy. That's the rectangular mnemonic. And today we saw that polar coordinates, if we integrate in polar coordinates, then we need to stick in an r there, and we very carefully derive this r using geometry. So that naturally comes out. If we have a triple integral dv, then we can use rectangular coordinates dx, dy, dz. And we saw that polar lends itself very easily to cylindrical coordinates by simply tacking on a dz. So that's cylindrical. We didn't have to do much geometry for that. For spherical, we need to do a lot of geometry, so I'll skip the details. Just like how r popped out when we were calculating the area, here we're calculating volume, and naturally if we do the calculation, we'll see rho squared sine phi to pop out. So don't ask me where this came from because I don't want to explain it. Yeah, but you know generically it's from calculating volume. And you should just use this formula for now. And then the three variables. And you can write them in any order you want, of course. I like to write them in this form just because theta often it's just from 0 to 2 pi, so you can pull it out easily. Right? And then you have a double integral to calculate. So that is a summary for today. Now next time we'll see how we can derive this rho squared sine phi part without using geometry. Right? That's it for today. Bye.